So I don't know if you know these debates that people will keep saying, well, machine learning is taking our jobs and we're going to give extent because of this. But then all of a sudden you ask it 1+1, it needs to reason that it's 3, for example, right? So we're talking about tiny machine learning and all of this fun stuff, but then we take 15 minutes to fix the project, right? So, okay. Good. So that's working at least. So we have already went through this type of 3 components of the course. And again, the first part is adding the combining the fundamentals, right? Like we want to cover the fundamentals of both circles, embedded and tiny machine, like machine learning. And then the part that's in between is the applications. And to understand why these 3 circles are important is we want to see if you combine both. And in the past, before tiny machine learning, people would in fact combine both, right? Like combining, for example, applications with machine learning, or maybe applications with embedded systems, right? Tiny machine learning is the intersection of the 3, right? But for example, if you combine this application with the machine learning, remember what I was telling you that this kind of wildlife tracking is a very old project, right? Many things have been done over the past 15 years, right? Even before the word tiny machine learning, right? Because again, you collect data from sensors. Remote sensors were already an industry before even machine learning booms up. And then you use machine learning on your cloud or in infrastructure back home to collect the data and process it and historical learnings, or you make things offline. So this kind of combining of applications with machine learning is already known. No one need to argue against it. You already know that basically it's very apparent everywhere. People are using it for a long time. But the key element that is missing there, it is not real time. It's not responsive, right? Like the idea of this is you collect data and then you use this data to take an application. For example, some of the projects we were working with in Canada is we're working with local transportation network, right? There are like those public buses that people use, right? And those buses follow a certain schedule. Good. So they have sensors on board on the transient network, and they collect the data. But they collect the data. This is like using this classical approach. There is a machine learning element into it. It's not real time. So I collect the data, and maybe once a month, once every year, or once a season when I need to change the schedule, I look into the usage behavior of users, which stations were more crowded, which routes were more crowded, and then I change my new schedule accordingly, right? For example, I'm putting in the schedule for 2026. I use what I learned from 2025 to apply and optimize my schedule, right? This is an offline optimization. This is a good use case. It's important, right? But as you can tell, it's not real time, right? Like I don't change the schedule, for example, if there is a traffic issue or if there's an accident in one of the routes and I need to send more buses there. I will not do it. My schedule is fixed over a period of time. I only take the feedback and apply it over a period of time. Good. So this is a classical application and machine learning kind of intersection, right? What is missing there? The real-time angle into it, because you don't really close the loop in real time. Good. So you don't really deploy much of the embedded system other than just collecting the data from the sensors. Good. So now, if you look into the other angle of if embedded and machine learning, they can vary on the spectrum. Like we can call, well, are you calling Raspberry Pi an embedded device or not, right? That's arguable, right? Are you calling NVIDIA Nano an embedded device or not, right? That's also arguable, right? It's an edge device, but are you considering it to be embedded? Well, NVIDIA's arguments for embedded and robotics and stuff, but it depends, right? This is also well, it's a good thing, but it's not what I'm looking for in the course, right? It's not the tiny machine learning angle, right? Tiny machine learning angle is taking it to the extreme, as we said before the break, right? So this is embedded plus machine learning in some more powerful devices. In mobile phone, for example, the example we give about the mobile programming course, right? There is a combination of this thing. And then applications and embedded, well, this is like a very old domain, right? Like people have been using embedded systems everywhere, right? Without much of intelligence, right? Which means traditional embedded systems weren't very demanding in terms of performance, right, and power. Most of us have played already with Arduino and big microcontroller, and usually they are very limited tasks. Most of the time they are bare metal programming. Like the typical example I used to give when I was teaching a cyber physical systems course is think of a pacemaker. Right? Do you know what's a pacemaker? A pacemaker is this device that is regulating the heart rate of people with heart issues, right? With cardio problems. Now, this pacemaker, a traditional pacemaker, is a very typical safety critical, right? Well, safety critical because if it has any fault there, well, you are risking the life of the patient, right? But it is not very high performance in terms of demand because the task is very basic, right? Only one application is running and it is regulating based on a very fixed rate. It's very predictable in terms of runtime, like cycle by cycle operation, and it is good, very well established in industry. Now, nowadays, pacemakers want to be more intelligent. I want to keep tracking of the vital signals of the patient. Maybe I adapt the regulation accordingly, whether you're sleeping or doing sports or maybe sitting in a couch. I want to adapt to this, right? This adaptation, as well as tracking, and maybe I have a Bluetooth connection to some sort of your mobile phone to send alerts to your doctor, this type of connectivity as well, right? What are we doing right now? We're introducing a lot of demands on that embedded system aspect, right? And because you are collecting a lot of data, you want to learn from it, you need machine learning, right? So what I'm trying to give you right now is that the intersection of these circuits separately has already been there for a while, right? But what is interesting nowadays, and this is the focus of this course, is the intersection of the three, right? So between these two, we have the example of wildlife tracking. Between these two, I'm giving you the example for pacemaker as an example. There's so many other examples, right? But then the combination of the three is what we are focusing on. You want to, I would say, revolutionize an application like healthcare, robotics, industry 4.0, UAVs like fully autonomous UAVs. It depends on like smart city infrastructure, energy sector, all of these things. You want to change them completely in a sense, using, this is the application side, using hardware, embedded very tiny devices already in field, and using machine learning that is running on those devices, right? This is what is the combination of all the three circles, which is tiny machine learning. Good. By doing this, we're excluding some of the work that is already done in other domains, right? For example, we're excluding classical machine, right? It is important. We want to use insights from it, but we want to change it to adapt to these constraints, right? We're also excluding the classical work of safety critical embedded systems because they're not intelligent, they're not very high performance. So we're using their constraints, but then we want to deploy machine learning. I'm going to give you a lot of examples. For example, one of the projects I worked on with the Barcelona Supercomputer Center, it was a European project that we wanted to deploy AI on self-driving cars, right? The problem with self-driving cars, the automotive domain, it's a very well-regulated domain. When I say regulated, there's a certification authority that you have to certify your car components before you put it on the system. Makes sense because, again, it's a safety issue, right? Now, for a very long time, a car was purely mechanical or mechanical with some electronic components, and the certification process was already known. Now, self-driving cars, or at least driver assistant cars that we have nowadays on the streets, you are collecting a lot of real-time data from cameras, lidars, radars, sensors, right? And this data, you want to allow the electronic component to take an action without the driver being involved. So like the self-driving aspect into it. The problem is AI is not explainable by nature, right? Like it's a black box. You take an action, well, how do you explain this? Well, it's the weights of the neural network with the magic internet, right? But what is the reasoning behind it? Why reasoning is important for self-driving cars? Do you know why I need to know the reasoning? Any guess why that's important?
Yeah. Because you need to know, you need to make sure the actions it takes are predictable. And without being able to explain why it takes certain action,
yeah,
no one knows who's at fault.
Yeah, that's the last sentence you said is very, very important, right? Who is liable if there's an accident, right? Assume that a Tesla car with fully self-driving capability is involved in an accident. Who is liable for that, right? Who takes the responsibility? Who is even at fault, as you said, right? Well, you can say the AI isn't at fault, but how do you reason about it? How do you prove that? Well, you have no idea why the AI took that decision. And this is the field of explainable AI, right? Or self-reasoning AI. Like it has so many names there, right? So now, this is just AI on its own. But you want to deploy this also in embedded devices because sensors and cameras nowadays they have in fact what we call local processing, right? By the way, one of the devices we would have for this course is a camera called the OpenMV camera, and in fact a camera with an accelerator on the camera itself, right? So you can really do acceleration of the vision without even needing to go to a microcontroller, right? Because the microcontroller, in a sense, is within the sensor. Good. So now we want to do this acceleration, and we want to take an action based on the camera feed we get. But this action, you need to reason about it. It needs to be in real time, and it needs to be safe, right? So how you combine all of this? This is a challenge that didn't exist before for classical machine learning, because classical machine learning was always on a server outside of the real-time loop. So you didn't want it to self-drive a car or be on a drone or something, right? So the action was more or less offline, similar to the transit example I gave you. But now the action is real-time on board and it's physical, impacting the physical environment. So you need to reason about it. Good. These are some of the challenges that we face. Any question or comment? Yeah.
And like, especially, for example, things that we don't use, like when we, let's say you report accuracy or one score,
Yeah.
we know that, for example, it has a component, let's say set false positives, for example,
Yeah.
false negatives. And if we deploy a certain like a safety critical scenario or an industry or a factory,
Yeah.
those things become very important because, okay, what if false negatives or what if false,
Yeah,
what
yeah.
if an alarm happens when something isn't there, or what if it misses something?
Yeah.
So then,
An excellent point. Yeah. How you ensure that this fault is within the accepted range of the certification, right? That's very, very important. And that's why also there is the term verified AI, right? How I ensure that I can build an AI system that I can explain if a fault happens. I can ensure that under all circumstances, the fault is within the range allowed by the certification authority, right? This is how only you can really adopt AI in real life use cases, right? That's the real challenge there. This is why up until now, we don't have self-driving cars on the streets. It's not because machine learning is not there. Machine learning is there, right? Self-driving software, I mean, it's open source. I mean, I know a friend of mine that in fact, he took his old Fiat car and turned it out to be a self-driving car with an open source AI, right? Yeah.
Lee, I have a question. So like, let's say you train a model, you use maybe an older version of sensor.
Mhm.
So across the time, maybe 2 years later, there's a new version of sensor.
Yeah.
So the sensor sensitivity is different, the tuning is different.
Yeah.
So you get a different message. Are we going to learn something to like denoising it?
Yeah. This is a good use case example. It's a little bit orthogonal to the course because this is more related to training or reinforcement learning, right? Which is updating your inference model on the fly based on new circumstances, whether these circumstances is a new sensor data or even a new situation that you are in that you didn't face before, right? It's one of the applications. It's one of the fancy applications. This problem doesn't exist only for tiny machine learning. It's a problem of originally machine learning itself, right? Which reinforcement learning is trying to solve. I don't think we'll have the time to touch on those. My hope is that the research component, the survey paper, is going to touch on some of these topics. But are you going to do this on the project? I don't think you will have the time. I mean, it would be fun if someone would try it, right? But it is a challenging task.
I was thinking like, I mean, I've been working on those. I mean, this is a typical data drifting, but
Yeah.
I was thinking if let's say it's an autonomous car, so maybe the car engine has been changed.
Yeah.
It's not a sensor, but
Yeah.
the application
Yeah.
per se has changed.
Yeah.
I think it was a very interesting.
Yeah, the environment has changed, or as you said earlier, the sensor might have changed. Or maybe over time, this is another problem, is that electronic components age. Like the sensor itself, maybe you didn't change the sensor, but over time, the sensor capability kind of ages, drifts, right? So that the accuracy or the way it gives you the output is a little bit offset. You need to recalibrate. How do you do this as part of the machine learning model, right? All of this would require either a complete retraining, which is the very kind of elementary way of doing it. But better than this, can you adapt the model on the fly, right? And again, I think reinforcement learning is the best way to do that. Are there papers on tiny machine learning for this? Yes, but they are still like very early phase, right? That's why it might be an interesting topic for a thesis. Any other question or comment? Good. So what I was saying before the question is, the technology is there in terms of machine learning. The problem is combining all of these also has a non-technological element, which is a certification or safety critical nature or the liability that would in fact prevent some of these technologies to be exist in our daily life, right? Those type of problems are more related to tiny machine learning than classical machine learning running on servers, right? So that's one angle that is very important to understand. Okay. So in terms of the hands-on experience, as we said, we're going to use the traditional machine learning pipeline using TensorFlow. And then, by the way, TensorFlow is not the only way you can do machine learning, and TensorFlow Lite is not the only way you can do tiny machine learning, but that's the easiest and most common way at the moment. Okay? We are going to use GitHub and Google Colab, and then finally, in terms of the third part of the course, is we're going to deploy this in the Arduino, like the device I just showed you. This is Arduino BLE Sense, which is a special Arduino. It's a little bit more powerful than the normal Arduino 8-bit, right? This is this is the microcontroller itself. So this is the one. Again, hopefully we are getting one for everyone to do the project, right? The nice thing about this one, this was called Sense at the end of the name. It's not only the Arduino microcontroller, but also a lot of sensors, as we'll see in the next slide, on that board itself. Good. And then in addition to this board was specially manufactured for the Tiny Machine Learning initiative. Well, it has the connections or the VCB, fact that you can connect the camera. This is the camera, you can see, directly to the board without worrying too much about connection, right? So this is a special board that was designed, I think, between EDX and Harvard and Tiny Machine Learning Foundation to enable doing tiny machine learning applications and teaching it in education without needing to wire in a breadboard, right? Again, that's not the only hardware available. In reality, I know people, and we have done tiny machine learning in the past on ESP32, right? You can do it in Raspberry Pi Zero, for example. Any microcontroller device should be able to run that stuff with some different capabilities, but that's one of the easiest to do, right? Any questions so far? So I'm mentioning this because if someone wants to use a different hardware, that's also okay, right? Again, in the lab, we have ESP32s. We have Raspberry Pis, but Raspberry Pi is not a tiny device. So I wouldn't really allow to use tiny Raspberry Pi only for the project, right? You can combine it with a microcontroller, and we have done this in the past for robotics. But you can use it to accelerate stuff, not to run tiny machine learning, because it's not tiny anymore, right? Yeah.
How power?
Yeah, there is a power source that it comes with the kit. You can put a charger, or you can
work without wire.
Yeah, there's a battery that you can connect.
Battery.
Yeah.
Okay, we do, for example, computer vision.
Yeah.
How long can that?
How you?
And will be the machine learning on continuously?
Oh yeah, okay, that's an excellent question. One of the very nice things of tiny machine learning, it's a fancy word that people usually use in papers and in talks, is that they say machine learning is always on, right? Why that's the case? Because you keep running the inference on the microcontroller in real time, right? If you're in a self-driving car, you don't want to turn off your machine learning, right? The same thing if there's a drone, right? So this is one of the key characteristics of tiny machine learning compared to classical machine learning. Classical machine learning is you turn on to run the inference and then you turn off. But tiny machine learning should be always on, right? Now that said, what if, for example, in Alexa, right, like or your Google, like your mobile phone, it's not always working in the background. It goes into what we call a sleep mode, and then you wake it up when you need it using OK Google or Hi Alexa or something, right? This is to save power, right? So always on doesn't mean that I'm always running in all applications. It depends on the use case. Some applications will always keep collecting data. Some applications can go to a sleep mode and only wake up when you have a certain trigger, right? You also have to customize or optimize for power consumption. Does that make sense?
So it works for this.
We will, in fact, in the sun, it works for this. It's sleep mode, and then you wake it up. One of the applications we will see in the second part is the wake up words. How you really program it. What's your name? Khalif. Okay, so you can say, you can program it and I would say, I'm Khalif, and then it wakes up, right? You can have a customized word that it will be able to recognize and then wake up accordingly, and then start running stuff in the background.
So,
It wasn't just some wireless verify itself, considered as cloud time.
Yeah,
For example, if we run like a large, like television model.
yeah,
On Raspberry Pi, would it consider that as tiny?
yeah. It doesn't mean that Raspberry Pi is bad. It means it's not a tiny device. It's outside of the realm that what people call tiny machine learning.
Okay.
Usually it is within the circle of edge AI,
Okay.
right? So, and it has its own use case. For example, when we work in robotics, microcontrollers are not enough. Because as you said, I want to run machine vision, right? You can do machine vision and we're going to see that application, but it has very limited capability. So if you want to run a very heavy machine vision with a very high definition camera, you need something more than a microcontroller, right? What you do in that case, Raspberry Pi or any other edge device, NVIDIA and are the most commonly used to. We have used both in the past. So for example, in a drone, you will find that there is a Raspberry Pi, usually we have the name companion computer. That's a companion computer that accelerates your sensor and machine vision. And then it sends commands to the microcontroller to control the motors and the movement and that's right. So both are combined in use cases, right? But what I'm saying here is that it is not part of the tiny circuit, right? It is an edge device, not a tiny device. Why? Because the way people formally define a tiny microcontroller is a sub-milliwatt device, right? It's something that operates in a battery like that size. Raspberry Pi would require something with more power, right? And again, it's also its size. It's a 4-core A53 or A57 based on which Raspberry Pi. It has a GPU, it has an 8 GB RAM, right?
Okay.
That's like a personal computer, right? Like it's very powerful. But that said, in fact, we struggled in the past to run, and someone was talking about YOLO here, right? Like you had, so basically we struggled in the past to run some of the YOLO versions on even Raspberry Pi, right? For example, Raspberry Pi 4, and I think we have Ahmed in the background that's also trying to do something similar. So Raspberry Pi is still a limited device, right? So if you want to run something like YOLO for detection on Raspberry Pi, you will face few issues. Your frame per second will become limited and you have to optimize stuff, right? Why? Because it's still an edge device, right? And again, people combine things like accelerators, like a Google TPU, for example, into it, and or a Coral Dev board. There is a lot of fancy stuff when it comes to edge computing. So it's not bad, but it's not part of the set.
Another question.
Sure.
Would Tesla be considered as tiny as well? I know it's big, but it's also like disconnected.
Which one?
Tesla, like self-driving car.
Oh, the SoC. Because this has its own SoC now, right? Well, it is an edge use case. Self-driving cars in general is one of the biggest use cases in the market right now for embedded machine learning and real-time behavior and safety-critical issues. It's in fact most of my research in that area. But it's not a tiny machine learning device. Some of that, because a car, in fact, is a system of systems, right? Some of the systems in the car are tiny machine learning. Because you have a microcontroller, for example, connected to the airbag sensor and only doing the airbag handling, right? That's a tiny device, right? But the whole system on its own is not definitely tiny. I mean, a car is not tiny, right? It's a big system. Yeah.
Doctor, just to add something on the YOLO.
Yeah.
When you want to run it on like microcontrollers and stuff like that, usually they make a tiny version.
Yeah.
Usually it has like a 3-scale detection
Yeah.
and the backbone, they remove 1 scale and they keep 2 scales.
Yeah.
That's how they.
Yeah, there is the tiny version of the YOLOs. That's correct. Yeah. But even with the tiny version, they didn't manage to run them in microcontrollers. I mean, if you did, then we should have a discussion. Good thing. But I think we tried the tiny one. It runs on the Pi. But if you try to scale it down to the Arduino, you still miss out. Yeah, because it's very limited. Yeah. Thank you. Any other question or objection? Some of you love the Pi, I know, right? It's a good device, but again, our focus is a little bit different. Now, in terms of sensors, I mean, this is the camera that I showed you here, and we are going to have some of the vision applications there. But then, more than this, the kit has a bunch of other sensors as well, right? This is the kit that I just showed you. So here, like this red bar, you in fact have some of the other related vision stuff. You have a color sensor, brightness sensor, proximity sensor, gesture sensor as well. And then you have a digital microphone that we're going to use for the speech and wake-up word use case. We have a vibration and orientation sensor, which is not a whole IMU, but a simple IMU in a sense. And then you have the stuff related to the environment, temperature, humidity, pressure sensor. And then you have the core ARM microcontroller itself, which is an M4. Right? So this BLE sense is in fact a very powerful kind of embedded, not powerful in terms of computation, but it combines a lot of sensors in one board, which enables us to run the course with a variety of applications. Good. So no matter what the project you want to do, this board can be a very attractive board if you want to do something interesting. Great. And again, we already mentioned a few of the applications. I mean, these sensors you can use in so many things. But for example, we already talked about the wake up word, the speech recognition, where we're going to use the microphone, the vision, where you can use the camera, and then the IMU. It's a simple IMU. What do you know when I say IMU, what I mean by IMU? Does anyone know?
Aerial measurement unit.
Yeah, it's basically a gyroscope and accelerometer, and sometimes people add magnetometer or not into it, right? So it's the IMU usually is used to detect orientation, right? Yeah, you definitely have it in your phone. If you ever wondered how you can really go into landscape mode versus the portrait mode in your videos, this is using the IMU because it knows how you orient your phone, right? IMU is very useful in robotics and drones because you use it for maneuver. Well, this board has as I said, a simple IMU. You can use it to detect. I think some work that they work with Dr. Tam. Dr. Tam does a lot of like signal detection stuff for Arabic sign language, right? So you can also use the IMU to detect that stuff. Okay, so to even make it clearer of what is really our focus, as we said, tiny machine learning is a sub area of machine learning, right? But even machine learning is part of a bigger area of artificial intelligence, right? Well, this bigger area of artificial intelligence, what else does it have other than machine learning? Why we say this is a bigger area than this one? Most of you have already taken machine learning courses that are experts more than me. So this bigger area, I mean, this is a superset, which means it has something else. What is this thing else? Can you give me an example?
Just a normal calculator.
A normal calculator.
It could be an AI.
Well, this is a good debate to have. Okay. From an angle, you are correct, because it does something that sounds like challenging. But when people talk about AI, they want to exclude this type of classical computing, right? So maybe let's have this discussion first, right? How, because according to your definition, anything that is used is that myself? Interesting. So what, like WhatsApp? Okay. So by your definition, any computer is an AI.
Yeah.
Right? Because a computer is both with an AI. How people are excluding normal computers from the AI definition? You know?
They don't take decisions on their own.
Exactly. So basically, they have pre-calculated decisions. A calculator would give you 1 + 1 = 2 because simply it was programmed to do that math, right? So, for example, and in the early days of machine learning, people were really mocking machine learning by saying it's a bunch of if statements, right? Well, which in part is true, right? So, but the key difference between machine learning and a bunch of if statements is you don't include all the cases, right? So you include some of the cases in the training and let it on its own guess the other case, right? So the key difference between normal computing, including the calculator, and artificial intelligence is you don't program the machine to do all the corner case decisions, right? You train it, and then some of the decisions are taken on its own, right? So this is good. We started earlier even from artificial intelligence, what to exclude outside, right? So you can put a bigger circle here saying computing system, right? And there, anything that is not artificial intelligence means it was programmed explicitly to achieve a certain task. Good. Now, within artificial intelligence, I'm claiming that there is a circle or a subset that is machine learning, and there's some other subsets. What is the data mining? Well, but data mining you can either program directly or use a bunch of machine learning, and hence, so data mining is orthogonal in a sense, right? It's an application that I can use machine learning for, or I can use normal computing paradigm to come for, right? Yeah.
There are the classical search algorithms, for example, and
Yeah, but this lies on the not the artificial intelligence. This lies on the traditional computing definition we just had, right? Because a classical search algorithm, a binary search, you include the binary search, right? Or you include the, I don't know, whatever linear search algorithm you include, right? So it's explicitly included. You don't leave if you left a corner case there, the computer will not detect on its own, right? So it's still a classical computing thing, right? Yeah. Reinforcement learning. Okay, great. So is reinforcement learning is part of machine learning, or is part of artificial intelligence outside of the machine learning?
Can be.
Yeah.
It's like a mix. It's common.
It's in fact part of the machine learning, right? Yeah.
That's the option. I think it's really important. It's not because I'm not research algorithms.
And
But search algorithms don't involve training, but they are
the latest one is
regrowth,
right?
right? They don't have learning on their own. Like they are not, they don't have that artificial intelligence angle.
There's animation.
Can we listen to our colleague?
So it's autonomous and can make decisions and it reacts to the environment. If you use search algorithm, you add a circle to the paths, let's say, it will behave differently. The path will change. So it reacts to the environment and it's autonomous. But there is a special thing about it, and then it's not training.
Okay, good. So how is this different from classical computing? I think you are arguing that search algorithms are a sense of artificial intelligence. But how this is different from classical computing? Because people knew algorithms, I mean, since early days of computers, right? What is classical computing? Yeah, okay, good. So as I was, your name is Khalifa, I think? Muhammad, sorry. Yeah. Again, I'm still learning. Okay. So
My name is
Muhammad has, okay, that's very easy to remember. Okay. So as Muhammad said, calculator, for example, what is classical computing? As I answered, or at least I tried to answer him, is classical computing anything that the machine will not behave outside of the boundary of how you programmed it, right? That's the key difference between that new world of machine learning and any program that they will have written in the past. Any program you have written, like using C++, Python, whatever, you identify the set of cases, and the corner cases, and all the behavior, and the program will not go outside of that behavior. So it has a very well-defined behavior based on how the programmer programmed it, right? In a search algorithm, binary search, for example, right? It's very deterministic in the sense that once you program it, any input you give to it, you know exactly what is the output because it's well-defined, right? If you forgot a corner case and you implemented it in a wrong way, then it will act according to that wrong way, right? Now, just to help you a little bit to think about it. Yeah.
Wouldn't personalized advertising might be a form of command
Okay.
or AI?
Good. That's an example of an application. Usually it's referred to as recommendation system, right? And I think in our department of Dr. Alex, that is expert in recommendation systems, offering an elective there. But recommendation systems is an application of machine learning.
Your
Okay. It's like a budget proposal thing. This is the one that I was talking to you about, like controlling the drones to hard disk power. Yeah.
was the robotics counts as artificial intelligence?
That's also another application, right? Like robotics is another application. Just to help you a little bit, can we achieve artificial intelligence without the classical machine learning? That's maybe the key question, just to help you decide.
Like, do you consider linear classifiers and SVMs as classical machine learning?
Yeah, but that's machine learning. It's different. That's the like the ABC of machine learning, right? Have you ever heard about neuromorphic computing, for example? Yes. Neuromorphic computing, right? So simply, like just to give you the history a little bit, machine learning, when it starts, like very early. I mean, there was a very early paper in, I think, 40s, but then Jeff Hinton in 80s kind of revised this and looked into it. Very early, when they looked into the intelligence for computers, there were two different paths, right? There was the path of let's try to faithfully model how our brains behave, right? Like build a model of the brain, right? And then there was this other path or approach of, well, we might really not need this. Let's build an abstract model into it, and this abstract model can evolve, right? Which one of these is machine learning?
The second one.
The second one. What is the first one?
Spiking neuromorphic.
Neuromorphic computing as a domain, right? So in that sense, neuromorphic computing is another example of artificial intelligence that is not machine learning, right? Why it's important to understand this? Because there are scientists in the world right now, there is a field, there is a domain of neuromorphic computing that tries to achieve an intelligence without the normal machine learning pipeline, right? Without really trying to have like a CNN or a neural network that's very deep, and that's trying to model how we really behave in our brain. Do we know exactly how we behave in our brain? Well, that's in fact the real problem with neuromorphic computers, right?
Still not-
We try to model as much as we can, but they're still a little bit far, right? So when we look into the bigger circle of artificial intelligence, neuromorphic computing is an example of that circle outside of machine learning. Good. Hopefully you're convinced. Some of you might not, but you can look this up, but it's good to understand the history of different things. Within machine learning, which is this abstract model, which is like, again, neural network, for example, we have machine learning as the bigger circle, and then part of it we have deep learning as an example, right? What is the key difference? I mean, above deep learning, we have neural networks, right? Because machine learning encompasses things that classical, as you said, linear regression, SVMs, and all these ADA boosts and all these classical. And these were the ones that at one point people think they are winning. But then at one turning point, neural network achieved very good results in terms of vision, right? And from that moment onwards, deep learning became the dominant factor of machine, right? So deep learning is in fact it's a subset of machine learning. Good. So if we go forward, you say that deep learning is in fact a subset of machine learning. Good. Why? Because there are other algorithms that are machine learning, but they're not deep learning. They're not neural network based, right? Usually people refer to deep learning as neural network based. Might not be necessarily true. I mean, it's a neural network that is deep, right? And what is the definition of a deep? It's a little bit a moving target, right?
Layers.
A lot of layers, yeah, inner layers. Good. Are we good so far? Now, when we say tiny machine learning, in reality, you can apply classical machine learning algorithms on a tiny device, or you can apply deep learning on a tiny device. And in the past, we have done research in both areas. Which one you think might be easier to implement in machine learning, right? Like in terms of compute power, I mean, linear regression and SVM is way less compute heavy than AlexNet and MobileNet and SqueezeNet, that stuff, right? So a deep neural network is very heavy in terms of compute requirement. That's why, in fact, they achieve good results, right? But they are very challenging for the tiny device, right? Most of the applications we will see in that course are mainly on applying deep learning into time. So when we say TinyML, don't get confused by the fact that we are doing classical machine learning, right? We are doing deep learning on the tiny side, right? And the reason I'm mentioning this now is because sometimes when you talk to people that are outside of the area of machine learning, sometimes they use the word machine learning only for classical machine learning, right? They oppose machine learning to deep learning, which is not necessarily true. Machine learning is the superset, right? You can use the word classical machine learning, in other words, to refer to something that is not deep learning. Part of that confusion is because deep learning became very huge, in a sense. Yeah.
Sorry, but can you just go back a little bit? So what would you say is the defining characteristic between machine learning and AI?
Yeah, it's because I said AI is simply the human goal towards achieving an intelligent machine, right? That's the bigger field of anything that you're trying to achieve intelligence from machines. And what defines intelligence? Well, again, it's a philosophical question, right? But in terms of computing theory, people kind of at least resides to the fact that you wanted to take an action on its own, based on some sort of historical learning approach, right? By that definition, you exclude anything that is very classical, well-defined. Again, any algorithm that is very well programmed, anything that we know that is not machine learning, that does not involve data learning, then simply that's not artificial intelligence, right? A calculator, a search algorithm, that stuff, not classical machine. But then what is the decision, like predefined decision making? But what is AI that is not machine learning? I give the example of neuromorphic computing, right? And because that's another domain, it's still alive up until now. There's a lot of research centers trying to achieve this neuromorphic computing. And some papers, if you read in neuromorphic computing, will argue that, well, right now we're talking about what they call general AI, what do you call it, GIL, right? I think Elon Musk or GAI. So this general AI, there's a belief for the neuromorphic computing researchers that it will only come from neuromorphic computing, not from classical machine learning. Again, it's still a debate, right? But it's another direction, and it's still alive, and there are research institutes that do it. Good. This is an example of something that is AI that is not machine learning. Clear enough? Now, inside machine learning, we also made the distinction that not machine learning is not something opposing deep learning. In fact, deep learning is part of machine learning. Because the way we define machine learning, anything that would involve learning from previous data building a model that behaves on its own later on in the inference phase, right? This applies to linear regression. It also applies to deep neural network. Then inside machine learning, if you're talking about a neural network, this became almost a field on its own because of right now that's the winning path, right? In reality, some of the, let's say, fallacy things in some domains that deep learning is a solution for every problem. That's not true. There are still some problems that are better solved using classical machine learning algorithms, right? Part of it is in tiny machine learning. One of the reasons is because it's very simple. If I can really achieve what I want using linear regression, a simple linear equation, why do I go for a deep neural network, right? So classical machine learning still exists, it's still applied. Up until now, certification authorities for safety critical system, in fact, they favor classical machine learning over deep learning because of its explainability, right? If you are deploying a linear regression model, you can know exactly what to expect compared to a deep neural network. So that's what defines machine learning versus deep learning. Good. So in that course, we're going to more or less, despite the fact it's called TinyML, we're going to focus on a subset of this, which is in fact tiny deep learning, right? Because most of the applications are using neural networks. It doesn't mean that you cannot use classical machine learning. As I said earlier, in some of our research in healthcare, we have used linear regression, SVMs, adapose, and all these classical stuff, and they give us good results. Did I clarify those things for you? Good. Makes sense now?
So, Professor, we're not going to use classical machine learning?
At least that's not the focus. You can use still in the project if you want, right? Still deep learning is more appealing for publication right now, right, than classical machine learning. It doesn't mean it's not really solvable. If you can identify a problem that you can solve using classical machine learning, well, that's great. Good. Now, this slide is just to say you might be using machine learning, in fact, without you knowing it. If you have a recent smartphone and you're taking pictures with your phone, you might not know this, but by the time you're taking the picture to the time you see the picture in your phone, you have already went through a machine learning model, right? Why they do this? To enhance the picture, right? Right now, they also enable you to really remove people from the picture, adding stuff and having a nice background. You wear a suit for a formal interview. All of this is post, right? After it. But even without doing any of this, from the time you take the picture, the snap, to the time you see it in your screen, you have already went through the machine learning model. Good. So we might be using machine learning without us knowing.
Like you can go to your photo app and search for something, and it will give you images with that thing.
For example, yeah, that's one of the applications that you might have to. How does it know? You have to really classify your images and be able to search with it.
I have the same thing, but when I name my contacts and add a photo of them, it also links their photos on my
Go
app.
to the contacts so that they appear when they call you.
And that only occurs when the phone is charging. It updates the list when it's charging, when the phone is charging.
In order not to consume the battery.
Yeah.
Okay, great. Yeah, so it's an interesting exercise to see how you might be using machine learning without you knowing. Well, you might also be using it when you shop in Amazon, right? Because recommendations, right, comes to you. How they come to you? Because they run machine learning on your behavior, your search history, even your likes on Facebook or Instagram. All of this is being collected and sold to companies. They are used to train models to try to sell products to you, right? This is how they make money out of it, right? Any question or comment? Great. Yeah, this is the recommendation example I was giving you. Great. So one of the applications we will see, and usually this is like the hello world of machine learning. If you have already taken a machine learning course, especially like a deep learning one or a neural network one, they will use image classification to basically show an example of a machine learning, right? Inside what happens in the neural network is you simply take the image as an input and you run through all your weights and activation functions, etc., until you determine whether this is like a cat or a dog or something, right? Object detection is another example. We talked about YOLO a couple of times before, right? If you are, for example, a drone and you want to detect certain objects, or you are in a self-driving car and you want to know whether there's a car in front of you, like a pedestrian or a cyclist, right? This is a stop sign, not a stop sign. All of this is object detection and image classification, right? So these are machine learning models that you want to. And then also segmentation, which is very important, right? Again, for self-driving cars as an example. I mean, robotics and drones similarly. Great. So another example is machine translation, right? And this is one of the very good examples of daily use cases. If you try, I go a lot for conferences, so I have used this in the past. In like all days when I was traveling, when I was a student, and you go to, I don't know, China, for example, or Japan, a country that you will not be able to speak English very easily on the street. What do? Right? It becomes very challenging for you. So you have to write stuff on paper and maybe show them signs or try to do some sign language, right? Or some kind of human common language. But then later on, when I don't know, joined academia and then start traveling for conference, I went to Spain at one point, and then I met a guy at the hotel that didn't really speak English. What did I do? I brought up Google. I started speaking in English, directly hearing in Spanish, and then the guy speaks in Spanish and directly hearing English, right? This is a direct example of, well, you do translation on the fly. How are you able to do this during runtime? Again, machine learning in the background, right? This is a more of a mapping problem in machine learning. You map from a language to another language using deep neural networks. Good. Again, recommendation is another example that we already talked about, so there is no need for this. Now, all of this are good applications, but we want to be able to run them, right? Classically, people assumed such data centers to be able to run machine learning, right? I have all the H100s, A100s, NVIDIA in the background to power my server, Microsoft Azure, Amazon AWS, and then I'm running my machine learning models. And I need to have connectivity to the cloud to be able to run them, right? Well, that's very, very big. And data center economy right now is a big problem. Everyone is talking about it, right? But recently, through a journey over the past, 20 years, we started having machine learning models that instead of running with data center, they are running on what we call accelerators, right? Google TPU is an example, right? Again, GPUs that you can purchase as accelerator cards in your PC are also another example. A year ago or 2 years ago, I don't know if you heard about NVIDIA SGX Spark, like this, I don't know, $250 personal supercomputer, like it's a supercomputer, right? It's something of that size, similar to your router size, for example. And it is literally a supercomputer. It's a data center at your home, right? I mean, data center in the definition of like 10 years ago, right? So things are becoming a little bit more consolidated, right? Smaller size, good. And this is kind of bigger is not always better. And why that's the case? Bigger is not always better. What are you losing if you are too big?
Power consumption.
Power consumption is the most important thing. Cost is very important thing, right?
Latency.
What else?
Latency.
Yeah, latency for cloud connectivity, that's a very important factor. Security and privacy is another factor, right? That we talked about.
Portability.
Portability, yeah, that's also, and for us, for example, in what happened? This projector keeps surprising.
I think it went to the end slide.
No, I still have, this is like 100 something slides. No, it's not. Okay. I just hope we don't take another 10 minutes trying to fix that. Let's see. Okay, good. Where did we go?
If you mean necessarily that you have a question, I've been kicked.
Yeah.
Is Apple AirTag considered as tiny or not?
That's a good question. So let's think about it. An Apple AirTag have a GPS connectivity, right?
Yeah.
But it connects through Bluetooth, so it doesn't really have a Wi-Fi on its own, right? This is if you know how it works, right? So for example, if you have an Apple AirTag, you bought it in your car, for example, or bag, but no one with an Apple phone nearby, you'll not be able to spot its location because it uses other iPhones to be able to make the connection through Bluetooth. But then does it run any machine learning model? Well, at least as far as we know, no, right? Maybe Apple is doing something, right? But you never know, right? So it's a black box for us. So because you don't run a machine learning model into the device, then it is a tiny device, but it's not a TinyML device, right? Good. Yeah, so we said bigger is not always better. We said so many reasons in privacy, security, portability, cost, right? Entry point to technology, right? This is why also I'm very enthusiastic about tiny machine learning because there are moments in technology where everyone gets a chance, right? So machine learning, because of all the cost needed, for example, again, like those very big data centers and the manufacturing of chips, like NVIDIA chips or Intel chips or whatever, they require a lot of infrastructure investment, which means whoever is ahead will remain ahead for it, right? But because of this tiny evolution of things, right now we have another chance to catch up, like as personnel, as countries, as domains of the world. So there is a democratization of the technology. If you read about like the politics of technology, people use this word a lot when they talk about tiny machine learning, right? They say democratizing access to technology, right? Why that's the case? Because cost is no longer a factor, right? Using, and I have another graph later on that will come in. Some of these microcontrollers, in fact, you can get them in Alibaba for $1, right? That's something very cheap, and it's cheaper than a coffee cup, right? And even the cost is becoming smaller. So cost is no longer a factor right now. And again, machine learning is again mostly open source. You can really deploy stuff there. So the challenge is really you ramping up and trying to deploy the edge of the technology and try to catch up with that domain. Right? So bigger is not always better for all these reasons, and this is why people started going from like data centers to accelerators, TPUs, edge devices, and then to mobile phones. Right? There's already some of you mentioned have taken the mobile computing course, and then. Well, you did already run TensorFlow Lite, so I had this as an example for you, but some of you already did it, right? You can run TensorFlow Lite in your mobile phone to detect things, right? Or even to do translation or to have like a question and answer exams. Yeah, again, the examples like high power, low power is an example. High bandwidth, low bandwidth, which is communication cost. Privacy, security, and latency are other factors. Then going from the mobile phone is not the smallest thing you can do, right? There are also some edge devices that you can compare to a mobile phone, Alexa, Google Assist, Google Nest, and some other examples. But then we go even what we call edge devices, like your wearable, something like a smart toothbrush, right? Something like your smart earbuds, right? All of these are very tiny devices, and in fact, they can be running machine learning models at them, right? So we try to go as tiny as, I will skip a few slides and then come back. Where did that go? Yeah, here, okay. So we want to go as tiny as something that is very small as all of these are sensors. So where is the microcontroller? Okay, so I'll just use the physical one instead of showing the picture. So we want to go as tiny as this one here, or even as tiny as like a coin-sized microcontroller, right? Which in fact you can deploy as smaller than like a tennis ball size, right? Why this is very interesting? Because you open the door for so many applications that were impossible. In reality, some of the modern applications that you can have a lot of economy and money out, and some startups are doing this. Is did you hear about like a smart football? Like that has machine learning into it, right? So there are companies that in fact do this, right? And why you make it smart? Collect data, right? That's really the goal of that age, right? What do you do with this data? Right? Yeah, to make more money. So make more money by winning games, by buying teams, and also by pricing players, right? There's a lot of economy in that sports, right? It's basically a capitalized market. And the data is the currency of that market, right? But also we use that basically instead of the VAR, right? If you have a smartphone tool and there is a goal, you can basically detect whether it's a goal or not, right? You have a camera on the goal, and then you have a smart device on the ball itself, and then, well, I know it's a goal or not for sure without really needing to look into it, right? There are so many kind of, I would say, a little bit less subtle applications in so many domains. Some of them are useful, some of them is to make money, but at the end of the day, you open the door for some applications that classical machine learning definitely wasn't possible, right? I wouldn't wait in a game to send the data to something, a data center, and then, I mean, this is very similar to stopping the game, looking to the VAR, and then come back, right? Good.
Also, there's an air pressure outside, sensor inside the ball itself.
Yeah,
To measure that it goes down, they change the volume.
yeah, if it's inflated, deflated from, yeah, that's correct. I think they deployed this first time in one of the World Cups like 8 years ago. Okay, so the key idea is, well, we already said this, like it's the currency of the current age, data, right? IoT devices are everywhere. And when you say IoT devices, these are smart devices connected to the world, right? There's also the fancy term of connected everything, right? And you collect a massive amount of data. There's some statistic that you basically collect 5 quintillion bytes of the, what is quintillion? I forgot how many zeros are there, right? So much zeros that you cannot even count, right? Every day from IoT device. In fact, data is very massive amount of data collected every day from everything. But the point is this data is not structured, right? And less than 1% of that data is being processed and used, right? And in reality, you might be very surprised of how people are not using the data they collect. I told you earlier before the break about that project with the local transit of Hamilton in Canada, right? You will be surprised what I'm saying right now, but this is in fact the truth. You have to believe me. They collected this massive amount of data from the buses. They put them in Excel sheet, and they do nothing with it, right? That's a very classical example of there is a massive amount of data, and basically don't use it at all, right?
They don't even sell it.
Well, whether they say, I don't know, right? I mean, they will not tell you. But I think because it's a public transit, they will not be able to, because if they sell, they go out of there. This is a data breach problem, right? They're not a private company, so they don't have the luxury of selling it, right? But the problem is you collect massive amount of data and you don't even use it for doing anything, right? For even getting money by optimizing your bus routes, right? And this is like, yes, it's an extreme example, but that's the example every day, right? Health data and wearables, well, getting wearables, most of us are doing, and your mobile phone data is collected from everywhere, right? And then this data is not used. Why it's not used? Because it's not very well structured, and also because of classical machine learning is very costly to deploy things such that you really get an economic benefit out of it. Now, if you use tiny machine learning with very small devices that are already on the field, I don't need to get the data out of the phone, send it somewhere to be able to use it. I will use it on the phone itself, right? I don't need to get the data out of the bus to go to a center and then use it. I will deploy it on the bus directly, right? So there are tiny machine learning is opening the field to use that data in a daily life, right? For good or for bad, it depends, right? But I can utilize the data because you have a real-time access to the processing. Good. So hopefully this motivates you to why tiny machine learning is very important, right? It can be scary at sometimes, but I think it's a good time to get into it because it's a field that's still emerging. Now, okay, are you guys done, or you still bear with me for a few minutes? Few minutes are okay. Yeah. So the reason I want to, maybe this is the first lecture, I know. I don't want to scare you from the course as well. Maybe I have already done. But the point is that next week I will be attending a conference in Abu Dhabi. I will be coming late, so we should start at 6 next week. I will send out an announcement on iLearn, and this is why this 1 hour instead of saving today, I will save to you next week. Okay, hopefully you're okay. I mean, speaking about logistics as well. I mean, Ramadan will be coming, so we'll have to at one point discuss what we do for the course. Most likely, what I was told is that we move to Sunday. But I will arrange with you what to do. Good. Okay, so we'll spend few minutes and then we'll conclude things. So how do we enable machine learning? We already said you combine expertise from 2 different things, You need to know embedded systems very well, and you need to know machine learning very well. And you need to know the challenges when you deploy machine learning in embedded systems, what happens. Good? So that's the flow of the code. Right? So combining these two gives you tiny machine learning. Yeah, we had some examples here. Now, if you take the audio as an example, as a set, right? What do you do in a machine learning pipeline? You take the audio input from the microphone, which is a sensor, right? Now, for a machine learning pipeline, the audio is your input, right? From an embedded system perspective, this is the sensor input, right? So if you were in an embedded system course, we do this in our 411, we interface to so many sensors, and you take the sensor data, you send it to the CPU to do something, and then have an actuator that takes an action, for example, right? Now, what is going to be different a little bit is that you send the data to the CPU, that thing that the CPU is running is going to be machine learning, rather than a very well-defined simple sequence. And then you want to process the input to do something. For example, if this was auto translation example we mentioned earlier, you need to translate. If this was to execute something, like you say, okay, Google, and you wanted to bring up and do something for you, then that's the other action you want to execute. This action is going to define your inference model in the machine learning language, right? So what defines the action here from a software perspective? It is the machine learning model you train, right? If you train the model to translate, then the deployment is going to be a translation. If you train the model to take a certain action to wake up, for example, that's the wake up action. And finally, based on the inference model, you want to generate an output, right? That's from the machine learning perspective. This can be the classification output, or if it's an object detection, that's the detection output. From the embedded system language, that's the actuation phase, right? Because in embedded systems, what do? You collect data from a sensor, you process, and then you actuate, right? That's the physical nature of dealing with the environment. From a machine learning perspective, input model is running based on the training, like that's the inference model, and then you produce an output. Good. So you take the output from the inference model, and then you take an action accordingly, right? This action is give me the translated text, or turn off the lights or execute the action. If it's an object detection, then I detected a pedestrian, then you have to stop the motor, do something. Okay. Now, as we said, how we collect our inputs, we need the embedded system knowledge to interface with sensors. Then talking about sensors, in embedded world, there are so many sensors, right? One of the defining elements, characteristics of an embedded system, we call it a cyber physical system, because you interface a lot with the physical environment, right? How do I do this? The ears and eyes of an embedded system are the sensors, right? This is how I understand the environment around me. Here in that kit, we have already discussed so many sensors. There are others, as there's an ultrasonic sensor that's very common in robotics, lidars, radars, infrared cameras, right? Night vision cameras, many kind of examples, accelerometers, compass, humidity sensors, another accelerometer, infrared emitter and receiver. All of these are examples of sensors that you can interface with. Who defines which sensor do I use? How do I know which sensor I need?
The application.
It's the application of the problem you try to solve, right? So you are the one, in fact, it's called the embedded system architect in embedded system language. The architect who designed the system is the one that's going to say, I need to collect that data from the real environment. This type of sensor is important. For example, if you talk about a UAV, then usually we equip a drone by like a camera, sometimes an infrared camera, right? Or a night vision camera. If this is a robot or a self-driving car, you might have a lidar or a radar to avoid obstacles, right? If you're talking about the healthcare domain, then your sensors become completely different. You have ECG sensors, BPG sensors, stuff to collect vital data, right? So the sensor is defined by the domain. Remember when I told you about the research verticals, right? We said there are fundamental knowledge, there's a system, and then there's the application. So the application defines what are your system components, including the sensor. Good. Yeah, we already mentioned so many examples of these. And by the way, like in our lab here, we have other sensors than these, and you are more than happy to come up with an application that would use some of them, right? Because we needed these sensors in our embedded courses anyway, so feel free to propose any sensor you want to use, most likely we'll have it. Yeah, this is an example of a biometric sensor. It's attachable to your skin. In the past, some of our research we have done is we used ECG sensor. You know that in your smartwatch, you might have an BBG sensor. It emits a light. If you wonder what is this light, right? It emits a light and then it measures your heart rate and all these things, right? Using machine learning embedded into your wearable.
Something that some diabetes patients they put as well.
Yeah, that's also correct. And in reality, there's some research. Can you train a machine learning model to use already existing BBG sensors in wearables to even learn something about the diabetes behavior, right? There's a lot of interesting stuff when it comes to what data you can use to detect which disease and that stuff, right? And again, we have active research area. And so if someone is interested in using BBG and ECG sensors or vital signal sensors to determine certain disease, this is something we have done in the past, and I think this is like an open area anyone can work on. Good. Then we talked about the sensor part. Then I need to process that data. So sensors, you need the sensor components, right? And then you collect the data to feed to the machine learning model. Now I need to process. Process means a compute element that runs the machine learning model, right? This is your actual microcontroller, right? This is the ARM Cortex M4 existing on the BLE Sense, for example, right? This is the Google TPU. This is the Raspberry Pi ARM A53, the GPU. This is an example of an NVIDIA Tesla GPU accelerator card, right? It's like a dive. This is a GPU, CPU. Then in your phone, you have an SoC that have a GPU, video processing, ASIC accelerators, multiple core CPUs, right? Again, some example of that chip in your, if you have an Apple phone, this is an A12 chip. What we want to highlight here is that in this processing component, if we go back to the use case, in this processing component, we had the data center, and then we had the accelerator cards, which are quite big. And then you have the chip on your phone, which is a bit smaller in terms of area. But then you have the chip in your wearable, which is even smaller, right? Still a multi-core SoC, but way smaller in terms of area. Here, like this is like 30 millimeters squared compared to 83 millimeters squared, for example. But what we are really looking for is something that is very, very tiny, as like an extremely tiny microcontroller, right? And the tinier you become, the better it is. I will show you once, I don't have this now, but I will show you once it arrives. This OpenMV camera, the camera itself, which is very small, has the microcontroller inside it, right? Something that I think was declared a couple of years ago, this Kinetics, like world's smallest MCU that is ARM-based. It was only 3.2 millimeters square. You can look this up. It was big in the news then. If you just compare its size relatively, well, the picture is not shown here, but they will have put it in literally like a tennis ball and see this is very, very small, right? You can really have it in the fingertip. In terms of shipments of embedded devices, we ship billions of devices of these every year, right? And the expectation is that they will become more and more, right? Because again, you will need to deploy tiny machine learning in everyday life. You need microcontrollers to execute this. So why the market is in fact evolving. In terms of the cost, okay, they're becoming very cost effective. A few years back, we were saying it's less than $1. The benchmark was 0.75 cent, right? Nowadays, we're talking about 0.5, like a half a dollar. You can really get a microcontroller. Put in mind that we're talking about the microcontroller, right? We're not talking about the full PCB, because I mean, the anything might be like tens of dollars, but it's not because of the cost of the MCU. It's because of the cost of the sensors, the bins, the interface, the PCB itself, right? But if you are a company, for example, building stuff and you manufacture your own PCB, literally the cost of a microcontroller for you is less than $1. Yeah, like comparing this to like a tiny battery, and we want to be operating with that battery. Maybe I will conclude by this because some of you are sleeping already. So what defines tiny for us in this course is, as we said earlier, you are a sub-milliwatt device, right? Anything that you're not very sure whether it's tiny machine learning or not, we will formally define this. It's a sub-milliwatt domain. If you need a battery that is more than definitely like a microwatt or a milliwatt, or if you are in the watt range, then well, it's not a tiny device. It can be an edge device, it can be a small device. I think the NVIDIA Nano is bringing 5 watt, right? And it's something that is very big for a GPU, right? Big, I mean good, like a very small power consumption. But still 5 watt is a lot for a microcontroller. So if you are sub-milliwatt, then you're a tiny device. If not, then you are an edge device. Good. And then finally, generate the output using some of the actuators. in your phone, you have the screen, and then in a robot, you might have like a servo motor. If we are doing some sort of a buzzer, for example, for a smoke detector, you have some speakers. All of these are output devices. What we call in the embedded wallet an actuator, something that gives you an output signal to the external world, right? In the airbag example I gave you earlier, I detect that whether this is a crash or not using a sensor. I process that data, and then what is the actuation action for an airbag? You open the airbag, right? So there's a mechanical component there that opens the airbag. This is your actuator, right? So this is your output. This is how we produce the output in a tiny machine learning. Good. Let's stop here. Thanks a lot for bearing with me. Remember that next week we're going to start at 6. Today's slides I'm going to upload them in iLearn, right? And the detailed like layout of the course and like milestones and stuff will be shared with you.